Hi, my name is Celeste Cunningham, and I'm doing my PhD at the University of Ottawa. Today, I'll be telling you about the occurrence and diagenesis of organic-rich strata in ancient deep marine levee deposits. Deep oceans are a unique geologic environment that hosts some of the most significant accumulations of sediment on the planet. Sediment is supplied to coastlines by the erosion of continental rocks in the hinterland, and by organic production along shallow shelves before being remobilized downslope into the basin by gravity-driven sediment flows. There's a few different types of sediment gravity flows, all of which are driven by gravity and by the density contrast between the suspended sediment-rich flow and the ambient seawater. These types are shown in the diagram on the top right, but in this talk I'll focus on one main type, turbidity torrents, in which the sediment is mainly supported by the upward component of fluid turbulence. A video of this type of sediment gravity flow is shown in the bottom left. These sediment gravity flows travel downslope through subsea canyons and channels until they eventually form a fan on the basin floor. Flows traveling downslope within these channels often spill out of the channel edges, as is shown in the top right diagram, and in doing so, they create wedge-shaped sediment deposits called levees that thin and fine away from the channel, as you can see in the cross-section of a channel levee system shown down at the bottom of the slide. There's many reasons why understanding the processes that operate in deep ocean basins is important, including natural resource exploration, climate modeling, geohazard assessment, and ocean pollution. Today, as you saw in my title, I'll be talking about organic content of levees, which has the greatest application towards the first 2 points, as turbine-ridden levees can form significant petroleum accumulations and can also affect the long-term global turbine cycle. Modern deep marine levees have been shown to sequester a significant proportion of the total annual global floods of organic turbine. An estimated 10 to 20% alone is buried in the modern Bendel fan, which is shown in the upper right. Because levees are extensive features that undergo high rates of sedimentation, they act as ideal sites for significant turbine accumulation and preservation, and as such, can act as efficient petroleum soil troughs. On the shelf, oxidation and respiration of OM remains in relative equilibrium with photosynthesis, which maintains balance between the consumption and release of CO2 and oxygen. However, when OM gets transported downslope by sediment gravity flows, much of it ends up spilling out of the channel and onto the levees, where the high sedimentation rates prevent its destruction by oxidation or respiration, therefore effectively sequestering huge amounts of carbon in the sediment. Significantly, this preservation can occur without special conditions, such as bottom water and oxid events in the ocean. Examining the distribution of OM in ancient levee deposits could provide insight into paleo-environmental conditions and the evolution of ancient ocean and climate systems, as stratigraphic intervals with abundant OM probably relate to periods of high productivity on the shelf. The deep marine levees in this study belong to the Windermere supergroup, which is a 6 to 9 kilometer thick succession of mostly marine rocks deposited on a passive margin after the breakup of Rodinia in the mid to late Neoproterozoic. The main topic that I'll be talking about today is how organic turbine is preserved in the levees of this system, as well as its diagenetic history. Fieldwork is conducted at the Castle Creek Study Site in British Columbia, Canada, while a Neoproterozoic succession of deep marine strata, including levee deposits, is exceptionally well exposed due to glacial pollution, allowing for detailed observations to be made at a wide range of scales. The methods I'm using to study these rocks include optical petrography and SEM-EDS, as well as geochemical analyses such as TOC and stable isotopes. 2 OM-rich facies have been recognized at this site, OM-rich mudstone and OM-rich sandstone. TOC in these facies ranges from approximately 0.1 to 7%. This is after they've been adjusted for the effects of low-oil green schist metamorphism, which is estimated to have resulted in the loss of 50 to 80% of the original oil-danite content. Oil-danite carbon isotope values in these samples ranges from negative 26.2 to negative 21.8 per mil. Because vascular oil plants did not yet exist in the Neoproterozoic, the potential sources of this oil-danite matter would be algae and phytoplankton, which is consistent with the measured isotopic values. The oil-danite matter would therefore be considered type 2. OM-rich mudstones are black, extremely fissile, and have an abundance of rhomboidal pyrite, as can be seen in these photos. They mainly consist of clay grains with minor amounts of silt. Sand beds with elevated TOC are usually highly cemented with plain and oil ripple stratification, and as you can see in these images, they have a distinct appearance that is defined by alternated bands of black oil-danite-rich laminae and orange sandstone. These oil-danite-rich sandstone beds are visually quite distinct from typical slope sandstones and mudstones, which are light beige and light gray respectively, as you can see in the top of this image. Oil-danite-rich sandstone beds are more common in the succession than oil-danite-rich mudstone beds. The oil-danite matter within these facies can be grouped into 3 types: discrete sand-sized grains, sand-sized organomineralate aggregates, or OMA, and nanoscale coatings around clay grains. The first 2 types are relatively uncommon, whereas the last type is quite abundant and constitutes most of the oil-danite content in OM-rich sandstones and almost all of the oil-danite content in OM-rich mudstones. Although OM-rich sandstones are composed mostly of sand, the black laminae, which is shown in thin section on the right and under SEM on the left, actually consist of highly concentrated clay grains that envelop sand grains. This is best seen under SEM, where you can see light gray bands of individual clay grains with abundant white pyrite rhomboids that encompass the sand-sized quartz grains. Most of the OM in these rocks takes this form, as clay grains surrounded by nanometer-scale black rims related to adsorbed carbon-rich films. This OM is interpreted to have originated as freely suspended micro and nanoscale oil-danite compounds and EPS from the upper water column over the continental shelf. These then became physically attached and oil chemically adsorbed onto the surface of clay grains, and subsequently were resedimented by suspension settling and active transport into the deep sea. This simplified diagram demonstrates how this process would take place. Panels A and B show how adsorption of freely suspended micro and nanoscale oil-danite material and EPS, which is shown in black, onto clay mineral surfaces, shown in gray, within the flow would protect them from the processes of oxidation and respiration. Panel C shows the hypothetical subsequent grain fabric following deposition, compaction, and lithification, which seems to match closely with the observed fabric in Levee mudstones. Although OM in these clay-rich bands is often difficult to observe directly, additional evidence for its presence is the abundance of the rhomboidal pyrite that I previously mentioned, which are the white crystals in the SEM images. Rhomboidal pyrite is microbially mediated and is formed from the degradation of OM in the presence of sulfate-reducing bacteria. Toluene, which is amorphous carbonate apatite, is also common in these rocks. The source of the phosphorus for these is the oil-danite matter in the black laminae. The next type of OM is more easily visible and consists of silt to sand-sized amorphous particles. This type is mostly found in the orange sand-rich bands instead of in the black clay-rich bands. The final type, sand-sized organomineralate aggregates, or OMA, consist of aggregates of OM and clay grains. This is a close-up from the left image showing the fabric of the OM and clay grains together. These last 2 types of OM are interpreted to be detrital grains sourced from disaggregated bacterial mats that grew on the continental shelf before being remobilized downslope. Also observed in these rocks are pyritized OMA, which are shown in these images. I've outlined them in yellow to make them easier to see. These grains consist of clay, mineral silt, and an abundance of rhomboidal pyrite, which indicates the initially high concentration of OM that was degraded to form these rhomboids. The next question to address is what is the composition of the interstratified oil sandstones, and what the association is with the OM in the adjacent clay-rich bands. As it turns out, these sandstones have an anomalously high intergranular porosity, up to 35%, that is filled with iron-rich cement. This cement consists mostly of fluoro and dolomite, as is seen in the above photomicrographs. Some siderite is also present, and is often seen as brown rims around dolomite crystals, although it can also appear on its own as small, brown, lozenge-shaped crystals. This table shows the diagenetic zones within compacted marine organic-rich mudstone sequences. The observed mineral assemblage in these rocks results from the progressive diagenesis of the organic-rich strata. Rhomboidal pyrite formed first during bacterial sulfate reduction. With increased depth, fluoro calcite and toluene would have crystallized subsequently. Diagenesis and dissolution of organic carbon and bacterial fermentation in the mudstones would have contributed both carbon to the cements and phosphorus to the toluene. The absence of sulfide would have allowed iron 2+, in addition to magnesium 2+ and calcium 2+, released from clay exchange reactions, to increase in coil water, eventually leading to the formation of fluoro and dolomite and siderite cements, accompanying bacterial fermentation and decarboxylation. In late-stage diagenesis and early-stage metamorphism, the fluoro and dolomite and siderite continued to form, with cations supplied from clay mineral transformations, such as the smetite to illite transformation, and from the dissolution and reprecipitation of previously formed calcite cements. The main takeaway from this is that the organic content in the black clay-rich bands plays a crucial role in the diagenetic history of these rocks. The next steps I'll be taking to better constrain and understand this diagenetic history will be to examine the inorganic carbon isotopes of my samples, as well as study the geochemistry of Levees as a whole and the stratigraphic distribution of these organic-rich beds within them, to see what I can determine about the paleoenvironmental conditions and the biogeochemical evolution of the ancient ocean basin. These results can also be used to improve our understanding of deep marine petroleum systems. Because levees are so efficient at accumulating and sequestering carbon, they have the potential to be economic soil troughs. Sandstone units within levees can also act as reservoirs, as can the related coil-grained sandy channel units that are in direct contact with levees. Depending on the geometry of the system, levee mudstones can also act as efficient seals and traps for hydrocarbons. In these ways, levees form potentially quite significant components of complete deep-water petroleum systems, and, significantly, don't need special conditions such as bottom water anostic events, or the continuous fallout of hemipelagic and pelagic sediment to form. The deep-water rocks of the Windermere supergroup may act as a petroleum system analog for continental margin systems, while episodes of high productivity allow for the downslope transportation of organic matter that may later form petroleum soil troughs. However, despite having high porosity and permeability at the time of deposition, early diagenetic cementation related to organic matter decomposition within levee sandstones can significantly reduce the porosity and the permeability prior to hydrocarbon generation. This would therefore reduce the reservoir quality. Additionally, mechanical compaction of the adjacent organic-rich mudstones would have reduced their thickness by up to 50% and lowered their porosity by up to a factor of 6. This highlights the importance of understanding both the depositional and the diagenetic history of organic-rich deep marine strata in order to aid in the assessment of hydrocarbon systems. So, to conclude, depositional processes in levees result in the concentration and enrichment of sedimentary marine organic matter. When the significant thickness and wide geographic extent of these levee deposits is taken into account, they represent significant accumulations of organic carbon. In levee strata, organic matter can be sequestered either in mudstones or in interstratified sandstones and mudstones, where they occur primarily as nanoscale carbon films adsorbed onto clay grains. A distinct diagenetic mineral assemblage is present in organic-rich strata that reflects the interplay of organic and inorganic diagenesis, which is controlled by increasing virial depth and temperature. Studying the occurrence of organic-rich levee strata and their diagenetic history will improve our understanding of deep marine petroleum systems and aid in the assessment of soil rock and reservoir quality in fine-grained lithologies. Thank you. I'd be happy to answer any questions that anyone has.